Okay, welcome back to class. This is going to be 5.2, interpreting graphs. Anything covered in this online lesson, again, has been or will be covered by Mr. Shang. If you have any additional questions, please email him or visit him during school hours. Now, the first thing that I want to explore here is this graph. Now, as you see here, there are increments on these graphs that on the bottom side go up by 10. So if each square here is going up by 10, I moved that. Let's do that. You'll see that these actually move up by 10. So right there, that'd be 10. Then you hit 20, 30, 40, 50, 60, and so on and so on. You gotta remember that the bottom x-axis has been time assigned as time is linear and is not the dependent variable. Distance has been assigned as the y value, or here as d and t, if you see. And we're gonna look at this curvature. Okay, Rowan is at the park with his dog, and the graph shows the distance from home as he walks the dog back home. So if we're gonna describe Rowan's walk home, when was he walking at a steady pace? So steady pace basically means a consistent change in distance over time. So if we look at the distance right here, this is from his house. So 0 would be he's at his home, and 3 would be the starting place. So if he's walking at a steady pace back home, the a value from our equation y equals ax plus b would have to be a consistent negative value. So this could be a decimal, this could be anything, but it just cannot be something that can't be plotted as of right now. So if we look at this curve right here, there's no way for us to tell what the curvature is or what the a value for that would be, because this is more of a quadratic equation or in that sort. Right here, we're going to be talking about a linear equation as we're going to look through in the next couple lessons. So the biggest thing, as we covered in last lesson, was a equals delta y over delta x. Now, if we look at this, we could measure both of these values. So from the top of this point to the bottom of the point right here, we could see what the values are. So change in y would be, if we start at the top, 3, and change it would be subtraction in this case. And then we end up going down. This is 2.5, 2, and this is 1.5. So we would go down to 1.5. That's our y value change. Now, if we look at our x, how much time is progressing, we will see that there is 1, 2, 3, 4 boxes, and perfectly ends on 40 minutes right here. So you'd start from our first value here, 40, or 0, and we subtract 40 from it. This would result in something like this, 1.5 over 40. Now, this would be our rate of change. And if you plug this into a calculator, you would get something along the lines of 0.3. And we could always round it to the second decimal place, as we did in the last lesson. 3.75, which would be rounded to that. Oh, no, that'd be 4. Now, it's really important that we remember our units in this case. So y would be distance in kilometers, and our x would be time in minutes. So this would actually result in 0.04 kilometers per minute. Okay, so this is steady pace. This is consistently moving this much every minute. Something like this, where it's curving, it means it's speeding up, and slowing down. So this was in this period, it wouldn't be exact. Now, if you look at this, when was he speeding up or slowing down? You could tell by the graph. So this part, he's walking consistently. This part, he probably stopped for a rest. This part, he started walking backwards. And finally here, you can see him speeding up, speeding up, speeding up. And when it starts flattening out and getting more straight, that means he's slowing down because there's less distance covered in the same amount of time. So we cut this box in half. You can see what's happening here. It's very steep. So almost 2 boxes per every 20 minutes. And this is like 1.5 box per every 40 minutes. And this is not even 1 full box, right? So this is changing slowly to speeding up to slowing down. Any other information that you would want to know? Again, right here, he is slowing. He is at a standstill as his distance is not changing over this time. Choose a section where Rowan is walking at a steady pace. At what speed is he walking in this section? Explain to a partner how you do this. Modify the graph so he's walking at a faster, steady pace. Now, we did this earlier. We took this part of the graph, we sampled it, and we got this value, which is exactly what you'd be doing for this type of question. Now we're going to move on to the next thing, I believe. I will be right back. Okay, as we said in the last lesson, there's a difference between discrete and continuous relationships, where discrete is just singular points where you don't know the difference, or there's no values in between the points. And continuous is where there are infinite values between them. So something like the number of people would be a discrete, and continuous would be like anything that has 2 dimensions, like 22 meters squared. That was an example provided in the last lesson. Extrapolation and interpolation is another thing to show what would happen in the future. So as shown here, you would be drawing a graph given only so many points, and then you would push the arrow out even further to see where it would be at the further x values. So since we don't know how far this, we don't know all the values here, not by data at least, you could extrapolate it by drawing an arrow outwards, finishing it there, and then wherever you want to know now. So let's say you want to know 40. So this is 20, 25, 30, 35, 40 right here. We look straight up and we get something here. If you extrapolate this data up here as well, you can match this up and it would be around 1 or 2 boxes. So this is going up by 10s every single time. This would go up by another 10, and we'd probably be around the same area. So we are at 90 and 100. So 100 degrees Fahrenheit would be about 40 degrees, or I think this would be 25, 30, 35, 40. Yeah, 40 degrees Celsius would be around 100 degrees Fahrenheit. Now, let me fact check that really quick because I want to double check all the answers. So yeah, the exact conversion here is 40 degrees Celsius to 104 degrees Fahrenheit. Okay. If we look at this, describe the relationship between Fahrenheit and degrees Celsius. We take any one of these points, let's say this one and this one. We do our delta y over delta x, and then it would be y1 minus y2 and x1 minus x2. Plug in our values. Y1 would be right here. Y is 70. Y2 is 50. X1 would be 20. And then this would be 10. 20 over 10, which would be just 2. So from this graph, as far as we could tell, if we just fudge the numbers a little bit, because you can see the points on the graph aren't exact, because this one's exactly on the dot, on the square right there. But if you look, this is not on the line right there. So it's a really important thing to know these numbers, or to recognize the fact that it's not exactly on the cross section, because if you look at this conversion, which was I did on a calculator online, this is not exactly times 2. This is times like 2 point something, right? So you need to look at the graph and you need to find data points that would match better. So if we had another data point like this really far down here, that would be on a cross section, that would work really well. Now, to talk about freezing point in Fahrenheit, you'd be looking at 0 degrees Celsius, right? Because that's the temperature that water freezes right here. And then we look straight up and see what point crosses. So that would be something around some odd 23, 21 degrees, 31 degrees Fahrenheit. If you extend the graph to determine what it was at 40, which we already did, you're around 100 something. There's a solution as the temperature increases, blah, blah, blah. Yep, linear relation. Okay, cool. So interpolate the graph by drawing a vertical line segment to the line graph at the 15 degrees Celsius axis and draw a horizontal line segment from that point on the f-axis. So that's the way that you find the data or what it relates to, right? Extrapolation, we covered that already. And now we're going to be talking about some definitions. Now, linear relations is a relation that is straight when graphed. So nothing like what we saw earlier up here. This is not a straight line. This is curved. Okay, so an intercept is a point where the graph of a relation intersects an axis. So as shown in this little picture right here, if we go up to this graph right here, the x-axis would be here. Let me just draw that right here. X, Y. Y-intercept is right here. X-intercept is right here. Because this is where, right here, is where the line crosses the X. And right here is where the line crosses the Y. Now, we already defined this to estimate the value, extrapolate, draw beyond. Now we're going to go through this problem and we're going to work on this. So let's see. We're just interpolating and extrapolating from data. We have these values and then we're plotting. It's plotted for us, so we don't have to worry about that, but we are extrapolating a little bit here. Describe the pattern and type of relationship in each graph. So if we look at this, this is straight, right? So as the salmon length increases, the girth increases in a linear relationship. Now the point tends to line up in a fashion which is pretty consistent, but we're not going to worry about that for now, right? As the length of the salmon increases, the mass increases in a exponential relationship. So you don't have to worry about that right now, but this basically just means that it increases in the graph until it basically reaches infinity. But in real life, that would not really happen because there's no salmon that's going to reach like 100 or maybe 1,000 centimeters. Then it'd be like super heavy, right? But we're not going to worry about that. So this would be exponential. And for these points, this graph is a continuous relationship and not a discrete relationship. Okay. Estimate the girth and mass of a Chinook salmon, which lengths are 90 and 125. So we're going to look at the mass and girth. So first we're going to take a look at the girth of 90. So 90 right here, lines up right here. This would be 50. So it would be around 50 for the 90. Now if we're looking at the 125, we need to extrapolate our data a little bit here and reach around some odd. This would be 40, 45, or 40, 50, 60, 70, 70 something, 77, 78, something around that. Right? If we're looking at girth or mass now, we take a look. Last one was 90. It'd be something around maybe 10 kg. And then if we're looking at 125, maybe something around 35 kg. Right? This is all what we just answered. And this is the last type of question, I believe. So pay attention right here. There's that little scribble or this little scratch type shape. This basically just represents that there are values before this, because you can't jump start to 1,100 and go 1,150, because that means that you would have to have gone from 150 like that all the way down. But since we don't have that, or since we don't have the room and the data is only starting from here, all you need to do is draw this line, and then basically you could just skip to the values that you want. Estimation of the speed of sound at each temperature. Take a look, -10 degrees Celsius, draw it up, interpolate, and you find around the range that it would be. 0, right there, 20, right there, -40, right here. Right? Cool. This is the homework that you should have done for this. If you haven't, please do it soon. That's it for today's lesson. If you have any questions, just please contact Mr. Shang.